Welcome to the machine learning course. Machine learning is everywhere. It has found its application in healthcare, retail, finance, education, and even agriculture. So what is it? And why has it become so important since the last few years? Well, very vaguely speaking, machine learning is making machines learn. It sounds very vague, I know, but that is what we want to do. We want to make machines to be able to think like us humans. Why is that, you ask? Why do we want to do it? Well, that's because we have a lot of problems that can be solved with data. And what has happened in the last few years is an explosion of data. We are producing petabytes of data every few seconds. And computers, which are very good at processing huge amounts of data in very short time, if they can be used to find patterns in this data, we can thus identify and solve problems. Thus came in machine learning to take us forward in this approach. But how do we do that? How do we make a machine do anything? By giving it a certain set of instructions, of course. Well, this set of instructions are called algorithms. The more complicated a task, the more complicated an algorithm becomes. Now, it's quite intuitive to think that certain types of tasks will have its own class of algorithms. If we want to work with musical notes, that set of algorithm will be different than the ones creating an animation. So, the algorithms to work with machine learning problems are called machine learning algorithms. Now, how do these machine learning algorithms work? What are they? How are they made? And how do they help us do anything? We'll get into it bit by bit. Let's start with a very small example. Say you're in a room full of 100 people. There are 60 males and 40 females. You have the record of the people in the room. That is, you have their height and weight. So each person has their height and weight. So these are the features of the person. They can also be called attributes. Now a new person is supposed to enter the room and you have been asked to predict whether that person is a male or a female using the data. And surely you have been given the feature values of the new person as well. Can we make that prediction using the data we have and comparing it with the data that we are given? Yes, we surely can. See, some kind of thinking is already happening in your brain. You are thinking, let me calculate the average values of the height and weight and compare it with the values we have. So if the height of this person is more than the average value and the weight is more than the average value than the average weight, this person is likely to be a male, because that is what we generally observe. Males are generally taller and weigh more than females do, right? So see, we are already trying to get to an answer based on certain conditions. What did we do? We took out the average values and then we are comparing that with the given ones, trying to get a probability of the possible answer. So what we are doing is conditional thinking, right? So now I'd like to take a break and drive your focus to these key terms over here, which are probability and the average values. Because you see, this is what machine learning algorithms do in their very core. They derive probability using some statistical factors. We'll get back to it in a moment. What were our statistical factors? So let's say we had 100 people in the room and the average height was 5.5 feet and the average weight was 65 kilos. And the unknown person, whom we have not seen, is 6 feet tall and weighs 90 kilos. So in this case, using our conditional thinking approach, we have already arrived at the conclusion that this person is highly likely to be a male. So you see, we did some kind of statistical learning here, right? And that is the very core of machine learning. The most basic machine learning algorithms are derived using the rules of statistics, and we will see how that happens in the upcoming slides. Okay, So what is the statistics that goes on here? It's called Bayes' theorem, and it was invented by a person called Thomas Bayes. And what is that theorem? It's on your screen right now. And don't get scared. Whatever the formula is, it is what we are thinking, and you will see how it aligns with our thinking in the next few minutes. So what does the Bayes theorem tell us? What we have on our screen is, on the left side of the equation we have py given x. The bar stands for given. So we want to find y, which is the class. That is, we want to find the probability that a person belongs to the class y, in our case either male or female because we have only two classes, given a certain feature x. If we consider only height, so what is our feature? Our feature is 6 feet. So given that the person is 6 feet tall, we want to find what is the probability that the person is a male, right? So py given x stands for, given x, what's the probability that it will fall into class y? And the solution is probability of that class happening. It's called prior probability. Py is the probability of the class multiplied by what is the probability we'll observe the feature in that class. P of x given y is that. So we know that we observe tall people in the male class more. So given the class male, we are likely to observe higher values of height, right? So our mind already does conditional thinking all the time. You see that? And then we normalize it by the probability of that feature occurring across all classes. We'll see how this goes on even in a deeper way just now. Again, I'd like to drive your focus to how this theorem is nothing but a model of our thought process. You see, why is probability of the class important? Why is py important? Why are we putting this into the equation? If you are in a room with 95 males and 5 females, and a new person was supposed to enter in the room and you had no record whatsoever of anyone, you could still say with a 95% probability the person is a male. So you see, what you're observing there, the class distribution is important. What is the distribution of the different groups that you want to observe? And then we want to know, given a new object, which group it will fall into. So what do? We take up some feature of that object, in our case the height, and see that in each group how much of that feature exists, right? So if we had just children as a class, not males, not females, just children below 5 years, the probability of observing 6 feet in the class children would be next to 0. So we could just eliminate one option of all the possible 3 answers in that case. It would just be adult male or adult female then. So what we do, we observe the distribution of the feature or the chance of that feature value occurring on the different groups. And then we want to see how much has that feature occurred. We normalize it using that. It is the normalizing factor is given so that the probabilities for all the different classes add up to 1. So now see how the ingredients of our thinking are put as the Bayes theorem. The Bayes theorem has 3 ingredients: the probability of the class, the probability of the feature, and the probability of that feature occurring in that certain class. The probability of the feature occurring in that certain class, group or category, whatever you call it, is called likelihood, which is px given y. And the probability of the class occurring in your population is the prior probability. So back to our example, we had a room full of 100 people and there were 60 males and 40 females. Among the 60 males, let us say there were 30 who were above 6 feet and 30 who were below 6 feet. And among those 30 who were above 6 feet, we have 20 people who are more than 90 kilos and 10 people who are less than 90 kilos. Among our 40 females, let's say we had 10 women who were above 6 feet and 2 of them weighed more than 90 kgs. Now you can see I have given it as greater than 6 feet, not equal to 6 feet. That is because we need to categorize our data into buckets. Now, if I consider just one particular value, like say 6.13 feet, that will probably be just one person having that exact value. So we have grouped our data as less than 6 feet and greater than 6 feet to make our calculation easier. Now, let us find our answer. What is the probability that your unknown person is a male, and use only the height attribute for that. So using Bayes' theorem, what we want to find is the probability of the person being a male given the height is 6 feet, right? Or the probability of the person being a female given the height is 6 feet or more. Putting that into the Bayes formula, it would be the probability of the male class multiplied by observing that feature in the male class, multiplied by the probability of observing that feature in the male class, and normalized by probability of observing that feature across all the classes. Well, we have 60 males, so that becomes 0.6, the probability of the male class. Now, what will be the probability of observing the height 6 feet or more in the male class, given that it's the male class? Well, we know there are 30 out of 60 people in the male class who are 6 feet or more. So there it goes 30 by 60, which is 0.5. And across both male and female class, we have 40 people who are more than 6 feet tall, right? Because there were 30 in the male class and 10 in the female class who were more than 6 feet tall. So that becomes 0.4, and thus putting these into our formula, these values give us the answer of a 0.75% chance that the person is a male. Now we want to find the same for the female. Yes, obviously it will be 1 minus the male class, because both the probabilities should add up to 1, like all good probabilities should. So for the female class, we do the very same thing. Anyone in that room has a 0.4% chance of being a female, because there are 40 out of 100 females. And how many among the females are more than 6 feet? Well, they're just 1/4. 10 out of 40 females are more than 6 feet. So that is 0.25. And then dividing it by the normalizing factor, it's 0.25. So say 0.75 and 0.25 add up to 1. And we have a good chance of reaching the conclusion that the unknown person is a male using only the attribute of the height. But wait, we have more values, right? We also have the feature weight. So if we use that, how will our answer change? How will our analysis change? Will anything change at all? Let's see. When we used only one feature, it's called univariate analysis. That is when you used only the height. Now we also want to use the weight. So we want multiple features, and such analysis is called multivariate analysis. So the same formula of Bayes' theorem for a single feature can be extended to multiple features, and that is probability of the class given all the features x1 to xn, depends how many features you are considering, that will be probability of that class occurring into, now this over here is important, it is the joint of the conditional probabilities, that I want to find the probability of the feature x1 and x2 occurring in the class y. This is the conditional probability. Like, I don't want just feature x1 or just feature x2. I want to see how many times both of them, in case we consider more features, we want to see how many times all of these features has occurred together in a certain class. And that is your joint probability. The pi sign stands for joint probability. The joint probability of pxi's in the class y. And then we normalize it by the probability of the features occurring across all classes. Now we'll see how this works using our example. What do we have right now? We have both the height and the weight. So we want to find the probability that the person is a male given the height is 6 feet, given the weight is 90 kg, right? That would be the probability of a person being male multiplied by probability of height being 6 feet in the male class and weight being 90 kilos in the male class, and divided by how many height and weight fall under this condition in the overall population. Well, we already know the probability of the male class, that's 0.6. Now, if you remember our distribution, we had 60 males, out of whom there were 20 who were both 6 feet tall as well as more than 90 kilos. So these set of 20 people fulfill both the conditions, and thus that probability becomes 20 over 60, or 1 by 3, or 0.333. And how many people are more than 6 feet and 90 kilos? Well, there were 20 such people in the male class and 2 such people in the female class, right? So that is 22 by 100, or 0.22. And putting these values in the formula, we get a probability of 0.909 that the person is a male, or a 90.9% chance, if we talk in terms of percentage, that the unknown person is a male. If we do the same thing for the female class, we'll get the answer to be 0.091, right? Because in the female class, someone being 6 feet as well as 90 kgs is an even less probability, because we know there are only 2 who are over 90 kilos as well as 6 feet tall. So this is where this huge difference is being created. So what changed? So right now, we are 90% sure that the person is a male compared to 75%. And we are even less sure that the person is a female. So our certainty, our vote towards the male class increased by a whole lot. So you see how including more features made us more confident, and how the joint probability distribution made all this difference. Now you might ask, how was any of this machine learning? See, we modeled our thinking into this beautiful statistical formula. We give the computer instructions to learn using that formula, using the data, and then arrive at an answer. We didn't hard code anything. We let the data guide us. And that is what machine learning researchers are doing day in and day out, letting the data guide you to the answer, processing it, modeling it using some formula, and then we get the answer. We did not tell the computer, okay, if the weight is between 50 and 40 kilos, it's a female. If it's between 30 and 20, it's a child. We did not do any such hard coding. We let the data distribution guide us, and that's beautiful. It's very simple, but it's very powerful as well. And this algorithm that we just did, which uses the Bayes formula, is called the naive Bayes algorithm. You just did your very first machine learning algorithm. Congratulations! In the next class, we'll see how to code it up in Python. From the very scratch, we'll see how the training happens from the data and how we can use it to predict a new value, and how we can test it to see how much correctly our model has learned. We'll do all of this and much more from next classes onwards. So tune in, and thank you for listening.